Welcome to the R video tutorial on the Central Limit Theorem in R. We're doing this via simulation. This is part of a series of videos. We have two prior to this, so you might want to go check them out before you watch this one. In the previous two, we dealt with continuous distributions. This time we're going to play with a discrete distribution and see how it behaves. Okay, so I'm going to keep the code that I had from last time. Notice we don't really have to change much but the population and maybe the limits on this picture. So I'm going to change this to a Poisson distribution. And the reason I'm changing it to a Poisson distribution is I want to see what happens. And a Poisson distribution only has one parameter. And here we know that this parameter is 7, which will mean the population mean will be 7. Notice this is the only thing I've changed so far. We're going to see what the histogram looks like and see if we need to change the limits of it. So give this a run and zoom in. We probably do need to change the limits of this a little bit. So let's crank this up to 20 here so that we get a good picture of what's going on. So I'm going to run this all again, get a picture, and we zoom in. This is a right-skewed distribution. The key thing here, though, is that the underlying data here are not continuous. They're actually numbers that are whole numbers, so they're discrete values. So if I were to come down here and just type in my data here, so which would be x mean, you can see all of them are whole numbers. There's no decimal places here. In the previous two videos, they would have all been decimal places, and I would highly suggest you go back and try it with those other videos and see what they look like. Okay, so the point here is there's gaps in this histogram. There are lots of gaps in this histogram because of it, and because they're discrete. There's no halves or anything like that. Okay, so let's see what happens in this case. Let's crank this simulations up. Maybe we can see a gap. I don't know whether it'll allow us to or not. Zoom in. Nope, still can't see the gap. But you can see it is right skewed and it's centered around 7, which is what we know it should be centered around. What happens when we start cranking up the sample size? So I'm going to go to 2 here. See what happens. Notice that it's already shrunk in and it's becoming less right skewed. Immediately, all we had to do was a sample size of 2. Notice that a data value out near 20 was likely, but a sample mean of, if we just took 2 samples and took their mean, 20 is unlikely. So let's see what happens when we go to 10. So when we go to 10, we get a picture that looks like this. And notice it's even less right skewed. It's centered around 7, and it's shrinking in. So it is starting to get a little bit symmetric. So keep that in mind. This is the Central Limit Theorem in action. You can actually see these pictures change. You can see it become more and more normally distributed. You can see that variance shrink down. Okay, so I'm going to say, what happens if I had 100? Let's just go crazy here on this video. We've played small before, but this is what it looks like. Look at that. That's pretty symmetric. It's stacked up at 7. So if I took a sample from my population of a size 100, and if the true mean is 7, it would be incredibly unlikely that I would even see a sample mean of 5 or a sample mean of 10. And that's what this is telling me. Is we can understand the properties of the sample mean using the Central Limit Theorem, which helps us make inference. And the point of this video is it even works for discrete distributions. So you could go back, and I would highly recommend you go back and change the Poisson to a binomial. Okay, try it with a binomial with an n of, I don't know, 1 and a probability of 0.5. And see what happens when you run this. You have to change the limits on your histogram from 0 to 1. But you will see, even in that case, the most extreme case where the data can only be 2 values, if you get a large enough sample size, the mean becomes normally distributed, and you can see that the mean shrinks in, and it stays around the true value of the population mean. All right, so we're going to keep moving on here. So I'm hoping you get a handle on the Central Limit Theorem because it's really, really important. That's why there's several videos on it. And there's also lots of other resources that you can find out on the web on the central limit theorem. And the interesting thing is you can actually prove this mathematically. All right, let's head off to the next video.